Alrighty. Hey everyone, and welcome to our HAPS Takeover, usually on Wednesdays, but this time it's Thursday, so it actually matches perfectly. Takeover Thursday sounds a lot better than Takeover Wednesday. And today we have our host coming on, Deanna Hooper, which will be sharing some amazing knowledge as always. Deanna was live earlier this week with I think it was an AMA about cosmology. May have missed a little bit of it. Sorry, Deanna. But without further ado, I'm going to go ahead and hand over the keys to her and her guest. Here you go.
Hello, everyone. Thanks for being here. It's great to be back on the HAPS account. Thanks to the HAPS team for having me here and for letting us do this takeover today. So for the last 4 days, I've been attending a cosmology conference. It started on Monday this week. It's going on until Friday next week, 2 weeks of cosmology conference. Now, there's about 350 participants at this conference, and usually at this type of cosmology conference, this is where the science really happens. Connections are made, collaborations are formed, ideas are exchanged. This is really where we get to do the fun things in science. We all love conferences. So this year, the conference organizers decided that we're going to share this process with more people. So we're doing several live streams weekly about the conference, just sharing everything that's going on, just to bridge the gap a bit between science conferences and people who don't get to attend science conferences. So without further ado, let's bring on screen the rest of the conference participants who will be joining me here today. Getting everyone on screen here. Hello, everyone. Great to see you here. Great to have everybody here. Okay, so why don't we just do quick fire rounds of introductions? I'll start introducing myself and then we go round so everybody in the comments knows who we're speaking to. And first, let me just say hello to everybody joining here in the comments. Lucia and Tanya, great to see you all. David, the other David, really nice to see all of you here in the comments. So for anyone who doesn't know me, my name is Deanna Hooper. I think I was already introduced. My name is Deanna Hooper. I'm a postdoctoral researcher at the ULB in Belgium. I work on dark matter and all cool things like that in the universe. And I'm a plenary speaker at the conference and also helping with all of the outreach and having great fun at this conference. Okay, let's just go around clockwise. So Sean, over to you.
Hello. Yep, I'm Sean Hotchkiss. My account name is Trenches of Cosmology because I have the idea of having this being a more general account with other people featured quite often. But I am an organizer of the conference, and I think I'll go into a bit more detail about how we're running it, but also a cosmology researcher. And I live in Auckland, New Zealand.
Okay, great. Alex, on to you.
Hi, everyone. My name is Alex Goff. I'm a PhD student at the University of Newcastle studying cosmology. I work on large-scale structures, so understanding how the largest things in the universe form and on dark matter dynamics. And I am giving a flash talk at this conference, but otherwise just attending and meeting lots of people and having some cool conversations.
Awesome. Daniela, let's go to you.
Hello, I am Daniela Sade, and I'm a research fellow at the Institute of Cosmology and Gravitation, which is in Portsmouth, UK. And I also work on the larger structure, and I try to understand how we can use it to learn about the energy and to also learn about whether there is any extra force that we don't yet know in addition to the ones that we do know about.
Awesome. Anna, you're up.
Yeah, I'm a postdoctoral researcher at The Ohio State University, though I'm originally from Barcelona, Spain, where I studied with Diana, the undergraduate of physics, and I'm giving a parallel talk in this conference, which is my first online conference through this pandemic, let's say. So I'm excited to follow these 2 weeks.
Awesome. So I realized I completely forgot to mention in the introduction the name of the conference and the idea of the conference. So this conference is called Cosmology at Home. And as the name would imply, this is done completely remotely. And one cool thing about this conference is instead of just taking the usual in-person format and throwing it online, the organizers took great steps to make this really feel as much like an in-person conference as possible. Personally, I've been super hyped about this conference for months, and so far it's been an incredible experience, and we're only 4 days in. So Sean, do you want to tell us a bit more about the philosophy behind this conference, why it's online, what are we doing here?
Yeah, I guess just in case people are going to Google it, it's Cosmology from Home. There is a Cosmology at Home, which is, I think, a citizen science project. So if you accidentally Google Cosmology at Home, you're going to find a really interesting site, but not the conference. Cosmology from Home is the conference. The motivation, I guess, comes down to essentially there are all these online tools, and I think in-person conferences are important and shouldn't go away. And once COVID's done, they'll come back and they'll be wonderful. But we should also be taking advantage of the online tools. So as Deanna said, we didn't just say, oh no, COVID has struck, let's copy and paste an in-person conference and just run those things online. We did sit and think. We actually were thinking before COVID even struck. We just got very lucky. Well, lucky is not the right word. Our thinking became more pertinent when COVID struck about how to use these tools to achieve what we want as cosmologists, as researchers, rather than just to do what happens in an in-person event. So I'll maybe mention 3 specific things that we've done that are slightly different. The first thing is that all of the official talks are pre-recorded and pre-watched. So they're not pre-recorded and then showed to people live. People watch them in their own time. And the motivation behind this is to allow the participants to only be at the computer live for discussions. There's no having to sit at the computer for passive just watching of a Zoom webinar, waiting for the chance to actually interact. So people can watch the talks while they're doing the dishes, while they're cooking, I don't know, while they're commuting, if people are commuting. And then that avoids Zoom fatigue. Everyone's always fresh. The second thing is that we have a virtual office space. So rather than once a scheduled discussion session is over, everyone just turning the computer off and going home, they're already there in this virtual office and then can disperse and talk to each other in different rooms. And then the final thing, maybe the most interesting thing for this audience, because I think that the previous 2 things are very interesting for the participants, but probably not interesting to a general audience, is we have officially scheduled time for themed discussions, but that's all that is officially scheduled in advance, just the idea that it is a themed discussion. We, the organizers, haven't said this themed discussion will be this themed discussion will be that. The participants can choose it. So not only is that then exactly what the participants actually find interesting that gets scheduled rather than us setting it in advance, but it's also what they find interesting during the conference. So if something comes up in a discussion session and it just doesn't get fully thought through, participants can suggest it and then it gets discussed. So hopefully in the next hour and a half, we can tell you about some of these themed discussions, which are literally during the conference, what the actual cosmology researchers have decided they want to talk about. There's been no in advance decisions that this is what they should be interested in. It's about what they actually are interested in. That's all I'll say about the organization, because I think the physics is probably more interesting to this audience.
And we did talk a lot more about the organisation in the first recap. So on Tuesday this week, we did the first recap of the Cosmo from Home, where we discussed days 1 and 2. Today, we are going to focus on days 3 and 4, Wednesday and Thursday, but of course, we'll also discuss other things that have happened this week. But I think that's one thing that I really like about this conference. I like the whole format of this conference. I already discussed the other day the nerves of pre-recording a talk and that you can do it an infinite amount of times. But I do like this format a lot. And this idea of themed discussions is really nice because it's really the community proposing a topic. Today, we've had, yesterday, sorry, I'm losing track of the days. Yesterday, we had some amazing discussions that were completely led by the community. Like, we want to get together and talk about this, and the organizers just allow us to do it. Kind of like HAPS allowing us to take over this channel just to talk about physics, which is amazing. So big thanks to the HAPS team for letting us do this. So you've all heard me and Sean talk about the conference already on Tuesday. So let's go around and hear some other opinions about the conference. Alex, what do you think about this whole online format of the conference?
Yeah, well, I mean, I agree with everything that both you and Sean have said so far. I was lucky enough to attend Cosmo from Home last year as well. So this is my second year, playing with this format. And I mean, yeah, everything that you've said is great. I like being able to watch the talks ahead in my own time and then only join, to actually be interacting with people. And there's enough downtime built into the conference in between certain sessions where you can actually, walk around this virtual space and have discussions with people rather than, just back to back Zoom meetings with no breathing room. So yeah, I'm having a great time.
Yeah, the lack of back-to-back Zoom meetings is much appreciated. Let's change the order a bit this time, Anna. Let's go on to you.
Sure. So as I said, this is my first online conference, but I had some collaboration meetings throughout the year, so I also appreciate the lack of back-to-back Zoom talks. And yeah, so this is one of the advantages, that you can organize your time throughout the day and watch the talks when works best for you. It's definitely at least harder for me to socialize online than in person, but I think this virtual space that we're using, so we're using a platform in which we have some cute little avatars that you can move throughout the map, and that makes it more real in a sense. So I think it's the best way one could organize an online conference, or at least one of the best ways to organize it.
And about those fun avatars, we discovered on the first day that you can actually put your avatar in the fire pit, because we have a virtual space that has beaches and pools and fire pits to chat around. We discovered at some point you can put your avatar in a fire pit, and there was a very engaging conversation going on, but it looked like all of the participants had ganged up to throw somebody else in the fire. We decided there is no cannibalism allowed at the conference, but it was funny to see that somebody's avatar was sat in the fire. Okay, Daniela, on to you, your thoughts about the conference.
Something that I like that is not unique to this conference, but I thought that was really nice. We have a code of conduct, and this code of conduct actually says very simple things like be decent, speak decent, act decent. So you may think, okay, why is this necessary? Well, the reason why this is nice and why this is also quite useful is that historically, science has been a very male-dominated, white-dominated, rich-dominated discipline in the West, at least. And slowly, this is changing. And this change has reflected in the fact that all people want to be treated well in order to have the best discussion possible. So this is always going to be better for science, because if everybody can discuss openly and share ideas, then truly the best ideas can come out. So this is why I really like the fact that we have a code of conduct saying everybody should be able to express their opinion without fear of harassment. And on this point, because, so obviously I don't know what all of these viewers are doing in their lab, but just in case there are some high school students, some young people, I would just like to say, if you watch the traditional media, if you watch TV, you may nearly always see that the scientist is someone who is regularly male, white, they've got gray hair, usually looking crazy, and a lab coat. It's usually the same lab coat. You wonder if at least they do laundry with that lab coat. It usually looks the same, exactly the same. Well, it turns out this is not what a scientist looks like. And indeed, we expect that the best science comes when there is equal participation to science. So if you're young, if you're wondering if science is for you, because maybe you don't look like the people on TV that are portrayed as a scientist, please know that if you've got that fire in you, you want to know why things are a certain way, you feel that shiver when you think about the universe and how it got to where it is, and are willing to work hard, well, in some sense, you've got already the scientist in you. So ignore the media, and we're really looking forward to welcoming you in science.
Thank you for that, Danielle. I think it's really important to make that type of comment. And I agree that the code of conduct is extremely important. I'm very happy that the Cosmology from Home Conference has it. I have seen gradually more and more conferences having this. Something I also want to mention is that there's clearly listed consequences if people violate them. Because sometimes you see code of conduct that's just like, we promise to be good. And that's it. And here it's clearly written, we will expel you if you're not keeping to the code of conduct. And I guess it is slightly easier in an online conference to ban somebody rather than physically removing them. But it is nice to see that there are actual consequences for people who will not keep to the code of conduct. And I have to say, at least what I've experienced so far, the conference has been extremely welcoming. There have been some really open, honest discussions. It's been very fruitful. It does seem like it's really a conference where we can just enjoy physics without having to think about other things that we might normally have to think about. So that was a great point, Daniela. Thank you for raising that. So we've mentioned already that we can propose topics, and the organisers, once the topic has enough support, the organisers schedule a discussion on that. So yesterday was day 3 of the conference. Initially, there was just themed discussions planned, and based on the input from the conference participants, there were 2 topics discussed. The first one was challenges that PhD students face beyond physics. And the second one was primordial non-Gaussianity in large-scale structure. If anybody was here on Tuesday, you might remember that we already talked about some talks about this, and this did lead to another discussion. But let's go first into this one about the theme discussion of PhD challenges beyond physics. So I'm going to open it up to anybody who wants to jump in here and talk about this. Alex, I believe you were involved in this as well, and you are the only PhD student on the screen here. So do you want to take initiative and tell us what this theme was about? You can say no, of course.
Sure. Yeah. No. That's fine. So yeah, the broad idea with this was PhD students face a lot of problems, partly related to what we were just discussing with the code of conduct. If you come from a historically underrepresented background in physics, so if you are not a straight white man, typically. But there are other issues as well. So the discussion that we were having was basically based into three different categories. So the first was about some of the bureaucracy that PhD students have to face, particularly if you are an international student. So sometimes, depending on where you are, different funding agencies may give you less funding if you're an international student, and you may have to do things like apply for visas every single year, which if you're a citizen of the country you're studying in, that's less of a problem. So that was the first topic. The second topic was about diversity in physics and what we can do to try and increase this. This is, again, coming back to some of the things we've discussed already. And then the third topic was about the initiative to try and get PhD students recognized as staff members of universities rather than students, because this affords them sort of some extra legal protections, being classed as employees rather than students, and also just from a recognition standpoint, the work that PhD students do is really no different than the work that more senior academics do. It's just that we are also learning how to do this at the same time. So from a recognition standpoint, it is nice, as well as some of the legal protections that would afford. So we had a bit of a discussion about some of the initiatives that have been running on that as well.
So I thought all three of those topics were really interesting, and there was a great exchange of ideas. I thought the last one, this whole idea about whether PhD students should be staff or students, was really interesting, and the point was raised that this changes a lot in different countries. And depending where you are, you're treated as one thing or another. So I did my PhD in Germany, where you are both students and staff in the way that you get the benefits of both. So you can still use your student card to get discounts at the lunch canteen, but you count as staff, you have a salary, you could join a union if you want, and you do have the rights that come with being a staff. They work it in a weird way where you're technically supposed to work 40 hours a week, but your contract stipulates that you work 29 hours and 52 minutes in a very German way. I remember that number because that is literally what my contract said. But you're supposed to work 40. So they have some things like that, but we did kind of get the benefits of being both a student and a staff, which was nice. So I'd be interested to hear how this was for other people. So Anna, you did your PhD in Barcelona, correct?
Yes, and in Barcelona it's the same as in Germany. I also was both a student and I had a contract to work at the research institute where I did my PhD. That in this case it was a bit different because in my university, that is also where I studied the physics undergraduate, is outside of the city, and so it's a big campus that also contains several research institutes. So actually I did my PhD in a research institute that is not part of the university, but they collaborate. So I was both a student enrolled in the university and I had a contract to work there. And yeah, I think this is the best option possible because you have the benefits of both, and you are still a student because these are also some studies that in which you have to enroll to university and pay for the course.
Yeah, Daniela, you did your PhD in the UK, right?
Yes, I did. And in the UK, we were students indeed. And I think in particular, international students potentially had to pay huge fees of the order of more than £20,000, I think. I wasn't an international student. I was considered a home student because I'm European. And at the time it was like so. My partner, who did his PhD in Denmark, he was a worker. So yeah, he was classified as staff. I should
Alex,
say that the
sorry,
fact that
go
we
ahead,
had, as part of, yeah, no, just to say, the fact that we had 3 PhD students discussing this as part of a conference was really interesting. It's the first time that I saw this, really.
Alex, you did your PhD. You're doing your PhD also in the UK, correct?
Yeah, that's right. So I'm in Newcastle in the UK, in the north, and I am classed as a home student, so I don't have to deal with problems with funding and visas. But I know several students who do, and it is exactly as you said, Daniela. International students still have to pay, exorbitant, in my opinion, fees to do PhDs and struggle to get funding from the same funding sources that home students do. So it's much more complicated if you are an international student.
Definitely. Sean, I'm not completely sure where you did your PhD, so
I
leave
did
that
my
to you.
PhD in the UK, and I was an international student. So, but I think almost every international student who's doing a PhD receives some form of scholarship that waives the international fees because they're just too large. I like some super wealthy people pay the international fees to be an undergraduate at some elite universities because then they, increase their job prospects. But I don't think anyone does a PhD to increase their business job prospects. So it makes it very difficult. You have to be able to win one of these scholarships. And I guess I come from New Zealand, which is quite privileged in that sense because there's various Commonwealth-based scholarshipy type things that allows one to come from here to the UK. And New Zealand is also a small population country, so the likelihood of an individual New Zealander winning such a thing is quite high. So yeah, I was an international student, but quite unique in that sense. And New Zealand never suffers visa issues. I guess we're one of the most accepted passports. So again, kind of privileged in that sense.
Yeah, I think this was a super interesting discussion to have, also just to learn about experiences in different countries and how something that I didn't have to think about in Germany and how people in the UK do have to think about it. Every country has its own rules, and of course this was something we discussed of any initiative we take. How do we do it in a way that every country's labour laws would keep to any initiative we take in this regard? So I think there's actually plans for a follow-up on that matter where only PhD students are invited. So not many of us will attend that, not many of us here on screen. But I think it's really nice to see this initiative. And there was another part that was discussed that someone in the comments has also mentioned here, Sania, that she doesn't think she's heard visa issues discussed before, but it's very true, especially if you don't speak the language of the institute where you're staying. And this is something that was also discussed a lot yesterday. There's so much paperwork involved in doing a PhD. And you often don't think about it, especially if you get all the forms in your own language. It's like, okay, it's just, another form I fill in, next. But this is a big issue. I'm lucky that I haven't had to deal with visas up until now because of Brexit. But it is an issue that a lot of people have to deal with, especially if it's not in your language. I can make a comment about that in Germany. So my PhD was entirely in English, and all official forms are in German. The official forms that you need to fill in to get your PhD are exclusively in German. And the 20-page PDF, which is the rulebook of how you should write your thesis and everything that you need to know about forming your committee, is exclusively in German. They provide a one-page summary in English that is not accurately translated and not legally binding, but you just have to figure out the German one. So that's fun. But I was lucky, of course, because I could speak to German students who have been through the process and they helped me with it. But I think it's something important to discuss, that there is this language barrier sometimes. I'm wondering if anybody else here on the screen has experienced this with official business having to deal with a language barrier. Does anybody want to give a comment on that? If not, we'll move on.
I had kind of a similar experience, but it wasn't an entire PhD, let's say. In my PhD, I didn't have that problem, though the forms are also in the local language. So international students also face problems in order to enroll to university and so on. Though there are translations in English, in order to ask for fellowships, they had to fill the forms in Catalan or Spanish, so they needed help to fill that. Personally, I had some visa problems in a 6-month stay that I did in Brazil. I had a visa for that stay, but then I had to register as a visitor, and apparently that's a very complicated process even if you're Brazilian, and everything was in Brazilian. And when I went there, it was really difficult because when I got there in person, they didn't want to listen to me, even though I tried to speak Brazilian because I can understand Portuguese. It's similar to other languages, but they noticed the accent and they didn't want to listen to me anymore because I was from abroad, and they didn't want to make any effort to try to understand me, and I had to go several times with someone local so that they could talk on my behalf and put pressure because there was a limit to do this paperwork, and it was really difficult to get it done. So yeah, that's the hardest issue I've had in terms of language barrier.
I think this is a super important topic. It affects a lot of participants. I'm not sure if we have the breakdown. Sean, do you know what percentage of the conference participants are PhD students?
Not off the top of my head. It'd be probably quite a large proportion, partially because the online nature means people with less funding can come compared to an in-person conference, and also partially because I think younger people are more willing to consider innovation, and therefore the fact that the conference is slightly non-standard will push away some senior people who are like, this is just too complicated, I can't be bothered. But I don't know. I could make up numbers off the top of my head, but they'd be made up, maybe roughly half, but I'm not sure. That could be way off.
Could be completely wrong. Order of magnitude estimate, we do that sometimes. But I think it was really nice to see a conference that its prime focus is cosmology, but it's also allowing us to discuss these issues that affect so many people within our field. And honestly, I've never seen this discussed at any other conference before. So this felt like a really big thing for me. So I was very happy with this. Now, before we move on to the second theme discussion, which was actually about physics this time, anyone want to make any final comments about this PhD discussion thesis we had yesterday?
I mean, I might just say this is tangential, which is why I didn't bring it up until now, but the online conference nature does allow PhD students from places where they just don't have funding to attend. So we have lots of people coming from places and say, places like Iran, not only do they potentially not have funding, but even if they did have funding, their credit cards don't work. So they just can't pay for a conference because of embargoes and things. And so, yeah, the inclusive nature of an online conference allows people with less money, which is biased towards PhD students, to come and interact. And PhD students are the ones actually doing the work almost all of the time. So they're actually the ones who understand the details. So you don't want to exclude them from your conference if you want a good conference.
Awesome. Thanks for that additional comment. It is important to highlight one of the many advantages of online conferences as well. Another one being the sustainability impact, that we no longer have to fly everybody halfway across the world just to attend a conference. But that's a whole other discussion for another day that I'm sure a lot of us are very passionate about. Anyone else here want to make any final comments about this theme? Okay, I don't see anyone rushing to unmute themselves, so I assume that everybody's satisfied with that discussion. So the second themed discussion yesterday was the idea of primordial non-Gaussianity in large-scale structure. Now, I believe this one was proposed after some very interesting talks on Tuesday, on the first day of the parallel and plenary talks, where this was discussed extensively. It was the topic of one of the plenary talks. Now, I did not attend this discussion, so I will leave this to other people. So who wants to take the lead and tell us what this discussion was about? Danielle, I believe you attended it.
Yeah. Okay. Yeah, under the spotlight. Okay.
Sorry.
So yeah. So perhaps first we may want to talk about what non-Gaussianity is. Yes.
Please, we tried to do that on Tuesday. I think we were somewhat successful. I was very happy that I was not the one having to do that explanation. I think we did a good job. Angaran and Sean did a very good job of explaining non-Gaussianities. But please, let's hear what non-Gaussianities are. Okay, in which case we talk about the discussion. So something that I wanted to mention
that I think...
No, I was going to say first, we should recap what non-Gaussianities are, because not everybody attended, and it's always nice to hear it from another perspective. So if you're willing to explain what non-Gaussianities are, please try to do so.
Okay, thank you. So first of all, the way we think the universe started is that there was a period where there was huge expansion, really fast expansion, and we call this inflation. And there is actually a lot that we don't know about this time. We know roughly how the universe is supposed to look like at the end. So we know after inflation happens what we want to see and what we need to see in order to make sense of the data. But we don't actually know a lot about what happens during this period. In particular, these are a few scenarios. One is that this expansion is driven by one particle that, in addition to making this universe expand really, really fast, is creating small perturbations here and there. And this is due to so-called quantum fluctuations. So this is because as you go to really, really small, if you imagine zoom in, and zoom in, and zoom in, and zoom in over nature, at some point you reach the scales described by quantum mechanics. And over there, nothing is really fixed. You've always got something fluctuating and changing slightly. Now, these fluctuations turn out to be quite important because they're really the reason why, in the end, we had seeds for what went on to form galaxies and clusters of galaxies and everything else. So these fluctuations are actually quite important. Now, as I said, beyond the basics, there is a lot that we don't know about inflation. And in particular, was it driven by one particle or more than one particle? And in particular, if it was driven by one particle, you expect to see something. And if it was more than one particle, you expect to see something else. If you've got one particle, you expect to see, a Gaussian universe, where Gaussian essentially means that you've got as many peaks as you've got troughs, and basically you've got that the perturbations fall a bell curve, and not unlike the curve you may have for the heights of humans. So for instance, if you take the height of the women in the UK, just because I happen to work in the UK, you will find that they tend to follow a bell curve, a curve around some average, and that curve tends to be a Gaussian. So this perturbation, these tiny seeds that go on to form everything we know, they also tend to follow a bell curve. So this is what Gaussian would mean. However, if you've got more than one field, more than one particle driving this inflation, the situation may become more complicated. And so this is why looking for non-Gaussianities can be really interesting, because it can tell you a lot about what happened or didn't happen during inflation. Before I go on, actually, does anybody want to add something before I go on to talk about the logical structure and non-Gaussianity?
I was about to say that was an excellent explanation. Very nice. I like the comparisons you made. Very, very clear. So yeah, anyone else? I think, Alex, you had something to add?
Yeah, I just had one thing to add to that. Again, excellent explanation of a very technical topic. I think one of the things that made this discussion particularly interesting is one of the things that makes non-Gaussianity difficult to detect in the late universe is that even if you start with a perfect sort of bell curve in the early universe, as stuff collapses under gravity and evolves, in the late universe, things no longer look like this bell curve. You have something that's non-Gaussian in the late universe. So when we look at galaxies in the late universe, if we want to detect whether the early universe was Gaussian or not Gaussian, we have to somehow disentangle the non-Gaussian stuff that was there in the early universe from the non-Gaussian stuff that happens because of the evolution. And that's one of the tricky things to do. And that was sort of one of the things that prompted this discussion.
Nice clarification, nice addition point there. Okay, so what was discussed? What was the point of this discussion? What were your main takeaways from the discussion? Whoever wants to take that, Alex, Daniela?
Yeah, so I will just say that this was focusing on measuring non-Gaussianity in the late universe. So even though non-Gaussianity is about what happened really, really, really early, it's actually quite cool because the consequences of this can last until today, even though, like Alex said, some really important point is that you have to distinguish between what happened at early time and the consequences as we find today, and what happened meanwhile due to entirely different things. It's like you had this it's like you had this picture of your great grandma, and over time the dust has settled over, someone spilled coffee and someone maybe took away one of the corners of the picture, and you're trying to figure out if this picture of your grandma when she was 2 years old was that of a child with a party hat. So it's quite difficult, right? Because it could have been the coffee having spilled and having made a triangle on the photo. So the point is, how come is the late universe good for this, even though it's an early universe thing we're talking about? It's because even though the effects are so confused among other things, for the late universe, we can look not just further away, but back to the past. So there is a point where the earliest universe we can look is given by the so-called cosmic microwave background, which so far is the limit, the furthest we can look. And this is the earliest possible, but it is just, let's say, at one particular distance and also at one particular time. This is roughly about 400,000 years after the Big Bang, so-called. Instead, if we look at it in the late universe, in the distribution of the galaxies, for instance, we can look at what happens over billions of years. And this is why we can collect a little information here, little information there, little information there, and place it all together. However, like Alex was saying, the critical thing is that you really need to disentangle between the consequences of early times and what happened meanwhile. And this is related to, I think this is also related to some other interesting concept that's valid for everyday life. The way people talk about the data, for instance, in the media, is as if data are immediately transparent and they tell you about facts. Data can be complex and they tell you about lots of things, one on top of the other. And it can require care to really understand what they're telling you. This is true for any kind of data. So the first, if you're presented with some data, one of the first things you want to do is, do I understand this data? Do I know what it's telling me? Can it be telling other things that look the same? And with this, I think I will pass it on to Alex, who can tell a little bit about the details. And I mean, I've tried to give some general picture with some vigorous hand waving that somehow makes everything sound more believable.
I love your analogies. The way you compare it and make it relatable to everybody, I love that. It's amazing. Okay, Alex, over to you.
Sure. I mean, yeah, I think you did a great job there. This is a very technical and thorny subject, so I commend you on your explanation. I think from the sort of technical takeaway that I had from this discussion was quite similar to what you were just saying, which is mostly that the systematics, this is a particular type of error that we get when we're measuring different things. And in the case of trying to measure primordial non-Gaussianity from the late universe, I think one of the main takeaways for me coming into this was that the systematics for this measurement are going to be really, really tricky to make sure we account for them properly and to make sure that we can sort of take them out so that any signal that we do get is true signal. And that's going to be hard to do, but it could tell us a lot about the early universe and be interesting if we can do that well.
Definitely be interesting. Sean, I think you wanted to add something.
Yeah, I unfortunately I couldn't attend the conversation itself because it was at 2 a.m. my time and the recording hasn't shown up for me to watch it. But I just wanted to add a few pieces of context because I think Alex and Daniela have done a really good job. But a few things that maybe can be added. One is that, so we had already measured this non-Gaussianity or attempted to measure it from this cosmic microwave background, and the constraints because of that show that it has to be quite small, which is another reason why I guess this is so difficult in the large scale structure, because we already know that it's very small. And all of the stuff Daniela was saying about inflation is relevant to those measurements, that it's kind of shown that any effects of any multiple fields must be relatively small. And the other thing that makes this very, very difficult is that things can be non-Gaussian in an infinite number of different possible ways. So even the constraints from the CMB are constraints on specific types of non-Gaussianity. But just like anything can be not a bear in a million different ways, it could be a tiger, it could be a tree, it could be a planet. Things can be not Gaussian in a million, billion, trillion different ways. So every time you feel like you've pinned it down, some model can generate a different type of non-Gaussianity, which means that if you're trying to constrain it, you have to just think and think and think about all these different possible ways.
Yeah, I just want to make a comment here. We've got somebody in the questions asking what is the difference between dark matter and dark energy. I just want to briefly say that today we are discussing mainly the conference. We will answer this question, but we are mainly discussing the conference. But tomorrow we do have an Ask Me Anything planned. It's going to go all day on Reddit. And then in the evening, some of us are going to jump back on HAPS and continue the Ask Me Anything. It will also be multicasted out to several different social media because HAPS allows us to do this. So if you have any cosmology questions, I'm sure Sean will share the link for the Reddit AMA if we have the link. I'm not sure if we have it, just if we do, please feel free to share it or tell us where we can find it. And tomorrow, I believe, same time as today, we will be back on HAPS for an AMA, and then you can ask all of your cosmology questions. So there's a question of what's the difference between dark matter and dark energy. Let's answer this briefly and then go back to the conference. Anna, do you want to take that question?
Yeah, so, well, they share a similar name, dark matter, dark energy, because we cannot directly observe them. So we know that these are components of the universe that we know they are there because of the effect that they produce, but we cannot directly observe them and we don't know exactly what they are. So dark matter is just the most accepted theory we have is that it's just matter that doesn't interact with light or with we're not sure if it interacts with baryons or normal atoms or not, but it's just matter that doesn't interact with light. So we cannot observe it by looking through a telescope. We know that it's there because it still produces a gravitational potential field in the clusters of galaxies, and so we have a very good estimate of the amount of dark matter in the universe, but we still don't know which particles compose this dark matter. And then dark energy is just the name that we call the responsible for the accelerated expansion of the universe, and the most accepted explanation, the simplest explanation that is the standard cosmological model is that this is just what we call a cosmological constant in throughout the evolution of the universe. But there are some other possible explanations for this, and we're still trying to analyze this great amount of data to distinguish between different theories, because we're still not sure about what is this component.
Thanks for that answer, Anna. That was a bit off topic, but I think that's a question we all like. And when I read that question, everyone was like, oh, I like that question. So it was worth answering that question. But back on topic, we've discussed the non-Gaussianity from large-scale structure. So does anybody here have more comments you want to make about this discussion before we move on? I'll just leave a few seconds, see if anybody else wants to talk about that. Okay, doesn't appear to be the case. I don't see people rushing to unmute themselves, which is always a sign that nobody has more to say. So that's what happened yesterday. Now, I do want to mention that apart from all of these scheduled events, even though we do have a lot of say in them, there is just free discussion time scheduled, which is just time where you're told, you can be online now, use a virtual conference space, just discuss if you want to. And I think it's nice to have scheduled time for discussion, because then we're more likely to actually sit down and do it. If you just stop the schedule after the theme discussions, a lot of people will go away. But you check the schedule and see, oh, currently I'm supposed to be just discussing with colleagues. Let me just wander around the virtual office and find somebody. And that's cool. And there have also been social events going online every evening. I have not participated in any of them yet, with a combination of setting up these broadcasts, my plenary talk, and the England game yesterday, of course. But I do hope to take part in the social events going forward. So that's what we did yesterday. It was a super fun day. Then we get on to day 4 today. Today was another day of talks, so not watching talks, because as Sean mentioned, we watch all of the talks at our own time. So we were watching talks in the morning, but not together. Everybody watches talks at their own convenience. But today we did have the discussion sessions for the talks. So I'm a bit biased today because one of these talks today was mine. So we did have the discussion of 2 plenary talks, the first one being my plenary talk on CMB probes of the early universe, focusing on CMB anisotropies and CMB spectral distortions. And the second plenary talk we had today was about the new CMB missions, the Atacama Space Telescope and the South Pole Telescope. So I guess, if nobody objects, I should start with a summary of my own talk. And I think I'm the best person to give the summary of my own talk, so I'm going to jump straight in and do that, unless somebody wants to cut me off. So I gave a talk that was
I think I do want to cut you off, by the way.
Please
People,
do so.
if you want to know what someone looks like that gives these amazing talks at these conferences where scientists meet, this is Diana, look at her, she gave a plenary talk today, and everybody liked it. Okay, I'm done.
Thank you, Daniela. I love your energy. Thank you. So you also made me lose my trail of thought, but that's fine. So my talk was about the CMB. So people who follow me on HAPS know that I love the CMB. We have a running joke that I can't go a single broadcast without flashing the CMB. And if I had the image ready, I would have flashed it now. But yeah, I got to give a talk about the CMB, which basically meant I was allowed to talk for 45 minutes uninterrupted about the CMB. I basically reviewed what the CMB is. So CMB, I'm throwing this acronym around. The CMB is the cosmic microwave background radiation. It's the oldest light you can see in the universe in any direction you look. It's basically just everywhere in the universe, and it's the relic left over from the Big Bang. So it really is one of the earliest things we can see in the universe. So my talk was what causes the CMB, what can we use the CMB for, how do we use it to constrain different properties of the universe. So I reviewed things like constraining dark matter, neutrino masses, inflation, all from the CMB. And this was focused on what we call the anisotropies. So these are tiny, tiny, tiny changes in a specific pattern. So if you have a temperature fluctuation or a temperature map, you can have these tiny anisotropies, which are little hot spots or cold spots within an average temperature. We have one for temperature, we have one for polarization, we have one for lensing. So I discussed all of the details about what these maps are, what they tell us about the universe, and the fun things we can do with them, but focusing on what has already been done in the past. So mainly I focus on the Planck satellites. The second part of my talk was about CMB spectral distortions. Now we know that the CMB is supposed to be a perfect black body. In fact, it is the most perfect black body we have measured, but it is not completely perfect. There are tiny, tiny, tiny deviations or changes from this perfect black body, which are caused by pretty much anything in the universe that just changes the energy slightly. So this is something that we last tried to measure 25 years ago, and we put a very good bound saying, okay, we didn't find a signal at this level, but we've never actually detected them. There are people in the community, including myself, pushing for a spectral distortion mission to go up and measure these things. And I argued in my talk that these spectral distortions are a treasure trove of information. It's just they're waiting for us to go up and measure it. And it's about time we send up permission to actually measure the spectral distortions. So the main takeaway from my talk was that the CMB is awesome, which is always a takeaway, and that it's told us a lot, but it's still got so much more to tell us. Yeah, that was my talk. And as always, I cannot talk about the CMB without getting passionate, and I love the CMB. But I'll pass it on to others so you can discuss my talk. Of course, you're not going to say anything bad because I'm right here, but I pass it on to others to discuss the talk as well. Anybody who wants to jump in?
I found really interesting to learn about the distortions, because this is something that is not as known as the CMB anisotropies that everyone knows and everyone uses, and so it's really interesting what information we could obtain if we could measure these spectral distortions more accurately in future missions. So this is for me, it was one of the most important conclusions of the talk, and I found it really interesting.
Yeah, I was really excited to see that you'd be giving this talk about spectral distortions, because this was actually the topic of the first piece of actual physics research I did, was working with someone on modeling the foregrounds, which are the basically nuisance things that get in the way of being able to measure these things for spectral distortion missions. And so it was really cool, a couple of years later to get to, hear a bit more about some of the state-of-the-art science that's going on with that now. So that was really exciting for me.
For me, it was really cool to see the different ways we have of measuring the CMB. And by the way, Diana flashed the CMB at some point. That is actually something quite remarkable. It's really, yeah, thanks, Diana. She's showing it again. That is a baby.
I don't need an excuse to show it, really. It comes up in every single one of my broadcasts without fail. So.
Yeah, so meet the CMB. That's a baby universe, really, really tiny universe that was just 400,000 years old. If that looks like a lot to you, remember that the universe is roughly 14 billion years old today. So that's really a baby universe. And these tiny, 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 tiny little things that you see here, whether they're red or blue, are these tiny variations, 1 in 10,000 really, that will go on to form everything we see. So if it wasn't for these tiny things we see, there would be no us talking today on Hubs, okay? Because there wouldn't be any galaxies, there wouldn't be any clusters of galaxies and so on. Now, the question is, how do you get to this measurement in the first place? And one of the interesting things that we discussed in the recorded talks today is that we are trying to take advantage of 2 main ways that really have complementary pros and cons. In one case, which is the one you can see actually, this blob you can see, you can send a telescope in space. You want to learn about space, space is a place to go. So you can build this telescope on Earth, then you launch it in space, it stays there, and it tries to take a picture of the oldest universe possible. And that's one way. The only problem with this is that by the time the mission is approved, by the time it flies, by the time everything is working, the technology has become old. So this is not the way to go if you want the really best technology, the latest cutting edge stuff. No, it's not. On the other hand, you can really look at the most sky. At the opposite side of the pros and cons, you can measure things on Earth. You can measure them on telescopes on Earth. And this is what the Akatama telescope that they talked about today and the South Pole telescope are about. In that case, you build a telescope on Earth and you've got opposite advantages. So you can have the best technologies, the best detectors, and of course, repairing something on Earth is much easier. But we've got that annoying thing called the atmosphere, which is quite useful because it helps us breathe, but it's annoying because it gets in the way of our astronomical observations. Basically, the Akatama telescope and the South Pole telescope are in 2 of the best places on Earth to observe. So the South Pole and the Akatama Desert in Chile. This is where the atmosphere is basically the best possible on Earth. But on the other hand, you can't see everything. You're not out there in space. We've got this annoying atmosphere, and also you don't see an entire sky because you can only observe the sky at night, which means you can only see that part of the sky that that particular place will see in an entire year. So just because of latitude, for instance, the Akatama telescope can see more sky than the South Pole telescope, just because of where it is, whereas the South Pole telescope has a cleaner sky. And I think Sean wants to point something, so I probably forgot to mention something.
Oh, no, I was just like indicating the Atacama sees more because it rotates, right? Because the Earth is spinning, whereas the South Pole doesn't rotate. It just is always pointing in the same direction. So Atacama can see a hemisphere, but then that hemisphere kind of rotates because it moves. And the reason these 2 places are the best are because they're the driest. So the South Pole's dry for kind of obvious reasons. The vapor just freezes out. And I don't know why Atacama is dry, but something to do with climate.
Well, it's a desert and it's in a mountain. It's a desert and it's in a mountain. So basically, for astronomy, deserts are good and mountains are good. So a desert in a mountain is double good. So this is one of the reasons why Chile has some of the best telescopes in the world. And by the way, I can see in the comment, we'll have a very powerful telescope in South Africa. That's absolutely true. So this is not about the CMB. This is the square kilometer array. It will observe the radio universe and it will gather lots of information. It's not just in South Africa, by the way. It's also in Australia, and is it in other places now? I'm not sure. Anyway, so it will observe the radio universe basically at a precision that we never could before. and it's going to tell us about a lot of things, including about the first stars, incidentally. But that's for another day, because today we discussed the CMB.
So I will not shut up about the CMB. I do just want to mention that, of course, I talked about my plenary talk, but there was a second plenary talk today, which was a joint talk given by a representative of the Akatama Space Telescope, the Atacama. I mispronounce that every single time. It's because in the acronym it's ACT, so I naturally say Akatama, but it's actually the Atacama Cosmology Telescope. So there was a talk today on the Atacama Space Telescope and the South Pole Telescope. This was a joint plenary, so we had a representative from each, and they split the time. And they told us about the next generation of CMB missions, so building upon the amazing legacy of Planck, what we can do going forward. And really, I can talk about the CMB for hours, but I do want to let other people talk as well. So does anybody else want to take the floor about the plenary sessions we heard today? Anna, I'm going to pick on you because I don't think you said anything about the CMB yet.
So maybe I'll say something about the other plenary talk about these Atacama and South Pole telescopes. So in some weeks ago, I think I presented on Diana's channel some results about the Dark Energy Survey. So the Dark Energy Survey is one of the galaxy surveys that is currently ongoing. So, well, it finished observations, but we're still analyzing the data. And this tells us information about the late universe. So we mentioned before that about the temperature and isotropies of the CMB, but also get information about the universe by looking at the CMB lensing. So this is taking into account, so light coming from the CMB gets deflated when traveling through the universe, through the distribution of matter in the universe until it reaches our telescope due to the weak gravitational lensing. And so we can also get information about cosmology, and in particular about the matter content of the universe and how clustered is matter. So we can get some information about the distribution of matter in the late universe by looking at these deflections of the photons coming from the CMB. And this is one of the other probes from which we can get information from these CMB observations that is even more accurate when using the Atacama and South Pole telescope. So there are very interesting projects that combine information from CMB lensing from these telescopes with galaxy surveys like the Dark Energy Survey, because they overlap. They are observing the same region of the sky, and since both of them analyze the distribution of galaxies or the distribution of matter in the late universe, we can combine all this information to get even tighter constraints on these components of the universe. So this is there are a lot of different projects combining this data in different ways, and this was one of the conclusions of this that talk about these telescopes, and is one of the most interesting. For me, it's one of the most interesting projects coming from these observations.
Yeah, I think the second talk today was really, really cool to hear about what they're doing with the CMB going forward. And I think it was really nice because it almost seemed like we discussed our talks in advance, because kind of my wrap up was what they started with. And I think that was great because we actually did not communicate in advance about our talks, and they just fit together perfectly. So again, congratulations to the organizers for choosing these two talks to perfectly match. So one of the main takeaways I had from the second plenary session was the how consistent the data from the CMB has been. So some people might have heard us discuss already on Tuesday that there's something known as the Hubble tension, where there's a disagreement in the expansion rate of the universe when we use the CMB to calculate this, and when we measure it directly with Cepheid and supernova. And there's been obviously some comments anytime there's a problem like this, we have to ask, is there a problem with the measurement? Did Planck satellite maybe do something wrong? One very nice thing is that the South Pole telescope, sorry, the South Pole, no, the Atacama one has found the same value. So they have basically proven that the Planck measurement was good, that the Hubble tension cannot be solved with just changing something about the CMB measurement, because now we have an independent measurement from a different experiment that reproduced it and has reached the same result. And this is always nice in science to see when you do a whole new experiment to do the same thing and you reach the same conclusion. It just means you can believe your results a bit more. So I, as people know, I'm a CMB person. I love Planck. And to see that Planck is kind of being validated by another telescope or by another by a ground-based mission, it's very nice to see. It's like we really know what we're doing in terms of CMB measurements. Sean, do you want to jump in?
Yeah, I guess just to pour a little bit of cold water on that they have a completely different device. So if there was something broken in the Planck device, certainly what you're saying is true. But if there's something we're not quite understanding correctly, it's quite probable that Planck and ACT and SBT might make the exact same mistake. So yeah, but it certainly reassures on some aspects.
Yeah, that is a good addition. I'm just going to ignore that because CMB is perfect. No, but it is a good addition that, of course, we are using the same overall idea behind it. So we could still be missing something in both cases. That is very true and a very good point to make. Okay, who else wants to jump in with the CMB? You should not let me ramble about the CMB without cutting me off.
Related to this, there was also like this a slight tension between with this S8 parameter, which is related to how much matter is clustered. There's a slight tension between this parameter is like the Hubble tension is not directly measured by the CMB, but you can derive this parameter from CMB observations, and this is the value that we obtain from the CMB observations is slightly larger than what is measured from these late universe probes like the Dark Energy Survey and other galaxy surveys. And so South Pole Telescope and the Atacama Telescope can provide also constraints on these parameters. And I think it was shown today that the value from the Atacama Telescope was a bit lower than Planck. So that will also be interesting in the future to see what happens with the combination of these telescopes with galaxy surveys, for example.
Yeah, that's also a very good addition to make. Sean, I think you wanted to throw a question at me.
Yeah, I do. So something that I've always wondered for a while is why the spectral distortions measurements that you were working on and talking about have taken so long to be measured. Because I think the COBE satellite, which was from the 90s, is the cutting edge. So I guess there's two questions: why WMAP and Planck? Maybe I or you can unpack what I mean by WMAP and Planck weren't able to measure this, and why we haven't made those telescopes able to measure it.
Yeah, so I will try not to just blame funding agencies for this. One thing that's important to differentiate here is that we often say that the measurement for spectral distortions was from the COBE-FIRAS mission, but we do need to separate it here because COBE was a dedicated CMB anisotropy mission to measure these temperature fluctuations, whereas FIRAS was set up specifically to measure the spectral distortions. So they were both on board the same satellite, but they measured very different things. So the reason why WMAP and Planck can't do this is because it's completely different technology. So if you build a telescope that can do both, you're not going to be able to put as much detail and resolution in both of them unless you have a ridiculous amount of money. So usually the more components you add to a satellite or to a mission like this, the more you lose in other aspects. So COBE-FIRAS was groundbreaking both for its measurements of the CMB anisotropies from COBE and the non-measurement of spectral distortions from FIRAS. But this measurement was 25 years ago, and what FIRAS told us is that spectral distortions are not above a certain level. So just to get a bit technical, FIRAS said spectral distortions have to be smaller than 10 to the minus 5. And I don't want to downplay this because this measurement was incredible and it really, really allowed us to progress a lot. So it was a great measurement for its time. It was 25 years ago. And we know that just within our standard cosmological model, we predict an amount of spectral distortions around 10 to the minus 8. So sure, FIRAS was great, but it was 3 orders of magnitude below where we needed to be, right? So It was great. It was great for what it was, but it's very much behind where we need to be. So as to the question of why haven't we measured them yet, because we haven't had a dedicated mission for this. Some people within the community have been pushing for this. I think there's been an increase in attention to this recently. At least from my perspective, I feel like there's gradually more and more people asking for such a mission. But it does come down to, at the end of the day, unfortunately, we cannot fund all science. So we do have to pick and choose which missions get funded and which missions don't get funded. And up until now, there just hasn't been support for a spectral distortion mission. I really hope today I convince some of you to help us get behind and join us lobbying. I do need to mention there is the obvious downside that a spectral distortion measurement is going to be very, very, very messy. There's a lot of foregrounds to account for. There's a lot of dust in the way, and it makes it very difficult to sell because, if I'm being completely honest, we cannot say with 100% certainty that we would be able to get rid of all of the backgrounds. So I like selling it as like, we could do these amazing things, but being completely honest, there is this issue of nuisances and foregrounds, and that does make people less inclined to fund such a mission. We have someone new joining us, so Katie, welcome. Thank you for being here. Great to have you on screen with us. Katie, do you want to introduce yourself?
Sure, yeah. My name is Katie Mack. I'm a cosmology researcher. I'm an assistant professor of physics at North Carolina State University. I'm interested in dark matter and the early universe and early galaxies and stars and a bunch of kind of weird stuff related to the end of the universe and things like that. So I had another meeting that I couldn't get out of, so I'm a little late, but I'm happy to be here.
Yeah, you joined while I was rambling about CMB, and if I don't get distracted, I will not shut up about that. So it's good that you joined when you did to stop me from rambling for several hours about CMB. So at the beginning, we all mentioned what we're doing at the conference and what our current thoughts are of how the conference is going. So do you want to mention if you're giving a talk, if you're here as a participant, and how you're finding the conference so far, Katie?
Yeah, so I'm not speaking at the conference this year. I'm really enjoying interacting with everybody and watching the talks, and I think the setup with the online space and Slack and the asynchronous talks and the real-time discussions works really, really well for a conference. So it's been great so far. I've enjoyed the chance to see what everybody's up to, and yeah, I'm looking forward to the next few days.
Awesome. Great to have you here. So we were just kind of wrapping up, I think we were wrapping up at least about the discussion of the plenary talks today. So Katie, I'm not sure if you were able to watch the plenary talks today or join the discussions. If so, do you have any thoughts, any takeaways, anything you want to say about these plenaries?
Yeah, I enjoyed your talk very much. I also was just getting kind of really excited about what ACT and SPT are going to show us. These the new data that's coming and how much we're going to learn from that. I also would love to see an update to the spectral measurements. I only recently realized that FireS was the last time we measured the CMB spectrum, which just seems very sad. I mean, this is the most perfect black body ever observed in the universe, and we've only looked at it once. So it would be nice to get a better view of that. And it was also really, I was really struck by your slides about how much more we can say about inflation now with Planck than we could with WMAP. And so, the inflation models that have been ruled out now that we didn't know about, or, we didn't have such good constraints on before, that was a really useful kind of reminder of how much we've learned. And I'm kind of hopeful that we're going to find something solid outside of sort of vanilla, flat universe, cosmological constant, cold dark matter. So it would be great to get those, a measurement of R. It and see the primordial gravitational waves if we can really manage that. And it would be really nice to see something weird about dark energy or dark matter. I have hope, but it was, you also made a good case that everything's looking very vanilla so far. So, I don't know. It was mostly, I think, I felt like the plenaries today were very much about, like, we might learn something really cool soon. We've already got a huge amount of information. Kind of let's see where this takes us.
I just want to mention, you brought up my slide on inflation. So this is a slide where I show what the bounds look like today. And we always zoom in more and more on our plot so that we can see what we're plotting. And I overplotted it with the bounds from just 20 years ago to show how far we've come. On the new bounds, you can barely see, they're just a tiny box on the screen. But I do want to say that I can't take credit for this idea. I actually saw my former PhD supervisor, Julianne Liskog, do this in a talk. And it was just mind-blowing to me, like, wow, we've come so far in the last 20 years. So I had to repurpose his idea, but I cannot take credit for that setup, because it was just, I think I even credit him on the slide, but it's just an amazing comparison. Okay, so I think we should wrap up on the plenaries. Does anybody have any other comments to make about the CMB plenary sessions today? I'll give you a few seconds to see if anyone unmutes.
I might just flesh out what I wrote as a comment, that this black body spectrum measurement by the FIRUS detector on COBE was kind of the final nail in the coffin to non-Big Bang theories, because before then the cosmic microwave background had been detected, but it could have kind of been caused by other stuff. It could have just been dust emission or something. But the Big Bang made a very precise prediction that this should be a perfect black body spectrum. And so then when it was measured to be, as you said, 1 part in 10 to the 5, a black body spectrum that kind of, within most of the community, caused them to stop thinking it wasn't a Big Bang. And I guess if someone wants to know more details about that, you can ask tomorrow in the AMA and maybe we can go into details.
Nice, thanks for that comment. Yeah, it's important to remember how important that FIRUS measurement was, even though we say, it's 25 years ago, it was still a very important measurement. Okay, so that was the plenaries today. Then we had 3 parallel sessions. So the idea of the parallel sessions, as the name implies, is that they run in parallel. Each parallel session has a specific theme. And usually within each session, there's 5 talks. Again, these are pre-recorded talks that we've watched in advance. And then we just come together live to discuss them. Now, of course, we can't be in all 3 places at once, so everybody had to pick a parallel session to attend. And I think actually with everybody here on the screen, we covered all 3 parallel sessions. So I do want to be brief about the parallel sessions. We cannot do justice to every talk. We cannot discuss all of the 15 parallel talks that took place today, or that we discussed today. So maybe we can just do one main takeaway that we had from each session. So Anna, what session did you attend and what were your thoughts and takeaways?
So I attended a mix of 2 sessions, but I just followed a bit the session about radio astronomy and the other one about large-scale structure. And they are similar in the sense that they want to get more information about the late universe. So these sessions, in general, we're talking about what observations can we make about the late universe galaxies or quasars, so going back to earlier universe, but this is still very late universe compared to the CMB. And the idea here that one of the ideas is that there are several ways of getting information from these observations and different types of observations, because radio astronomy, for example, so this would be looking at the radio emission from those quasars, for example. And by combining all these different types of information, you can get even more information about the universe, the components, and also even about these non-Gaussianities coming from the early universe. So this is, I think, very interesting. And yeah, I don't have a conclusion about the talks, but they were really interesting in general.
Awesome, thank you for that. Sean just reminded me that I forgot to mention that, of course, I've been talking about the ones that I've seen or that I've attended, but this conference also has late time sessions, which take place in the middle of the night for me, but which are better for other people's time zones. And since the last recap, there's also been some late time plenary session, parallel sessions, sorry. So maybe we can also discuss those. So Daniela, on to you. Did you attend the parallel session? Do you have any comments to make about it?
Yes, I did. So I attended part of the large-scale structure session and part of the dark universe session. And I'm just going to mention one big idea. So rather than speaking about, the details of one of the talks, I would just like to mention one of the big ideas. During let's say the past 10 years, people have realized that we could test for dark energy in labs. Yes, that is true. You've heard it correctly. Even though dark energy is something that makes the universe expand really fast, in some cases, you can make tests for dark energy with a tabletop experiment. So one of the talks also discussed part of this and what you can infer. But I think it's one of the coolest things we've been able to do with science. And maybe if there is interest at the Ask Me Anything, I'll talk more about this. So I think I think this is really one of the best ideas that I would like to mention. The fact that at least for some of the models of dark energy, we can actually make experiments here on Earth.
Had to refine my unmute button. Thank you for that. I think it's incredible to think how we can test such a thing here on Earth. It's really amazing. Okay, Alex, we haven't heard from you in a while. Did you attend the parallel session? What were your thoughts? What were your takeaways?
Yeah, I did. So I attended the large-scale structure session because that's the subject of most of what I focus on during my research. And yeah, there were a bunch of cool talks. Without going into details on any of them in particular, because we don't have time. There were several neat ideas. For example, one of them was about how we can measure the growth rate of how quickly structures in the universe form by constructing maps of how things nearby to us in space and in time are moving around. So by constructing these velocity maps, that helps us understand how the universe forms over time. Was one of them. There was another talk about how if dark matter interacts with normal matter in a particular way, how this shows up as a set of bumps in a particular statistic that we measure a lot in cosmology, and how we might be able to detect that and what implications that might have. So lots of really neat ideas, and it's just nice to hear about these and chat with people about them during the session and afterwards.
Awesome, thank you for that recap. So Sean and Katie, I believe you two attended the evening sessions. So Sean, let's start with you.
Yeah, I have two things I wouldn't mind talking about. So I don't know if Katie wants to go first, because maybe I'm about to say the same thing she was going to say, and then I can say the other one. Or so there were two talks I found kind of interesting in the late session that we both attended. One was trying to resolve this Hubble tension essentially by changing the mass of the electron when the CMB was being formed, which was quite interesting. So perhaps people have heard before that the Higgs field gives particles mass. I can't go into detail about how it does that, but the way that they had their model was by having the Higgs field having a different value in the past, and that meant that the electron mass was different, which would mean that the CMB would form at a slightly different time, which means the age of the universe is slightly different, which means the expansion rate today should be slightly different. People have tried that in other ways before, and it hasn't worked. So these guys had an additional fact, which meant that it did work, because the normal way of doing this causes other tensions to get worse, and these guys were able to overcome that. So that was quite interesting, thinking about the fact that the electron mass might vary in time, and that might be what we're measuring with this Hubble tension. And then the second thing was there's a mass gap of black holes that shouldn't form due to astrophysical reasons. And now my astrophysical knowledge is not great, so I might butcher what I'm about to say a little bit badly, but when you get to a certain mass of star, it can't get any more massive because certain astrophysical processes cause it to lose mass. To do with nuclear physics, I don't know the main details of, but what has happened is that LIGO and Virgo, gravitational wave detectors, have detected collisions of black holes that are kind of just above where this mass limit should be. So either they're just rare events, or there's something not quite right in the astrophysics, or this is evidence of new physics. So these guys were talking about a particular new model of beyond the standard model of physics that would cause the stars to lose mass more slowly, so that therefore they can get above this mass limit and then form black holes that are then above this mass limit. So I found that kind of interesting, because it's not what we normally talk about in cosmology. Normally it's always about density perturbations and the CMB and this and that, but this is like actual stellar processes that might be giving us evidence of new physics, which I found really cool and just not what I'm used to thinking about.
That's awesome. Katie, what about you? Do you want to talk about some evening sessions as well?
Yeah, so I was in that same session, and I was also quite intrigued by sort of both of the same talks. But the thing I think is really interesting about the black hole mass gap stuff is that, you know, we're at the point where we're starting to see a lot of these collisions of black holes, and we're starting to see enough that we can actually understand something about the population of black holes, and at least the population of black holes that collide with each other, which is not necessarily the same, because you could have some that are formed singly and some that are in groups, and those might be very different. But we're starting to really have enough of these black holes to learn something about the population, in the same way that, you know, we're starting to have enough planets around other stars, extrasolar planets, to learn something about, in general, what planets are like. And so we're learning how, like, what kinds of black holes exist out there and how they interact with each other, and that's challenging some of our assumptions about how black holes form, which is the same thing happened with the planets. You know, we kind of thought we knew what a solar system looked like, and then we started discovering all these like really massive planets really close to their stars, and that sort of changed how we thought about solar systems. And so now we're seeing, you know, we're thinking about black holes differently, because we're seeing these really massive black holes colliding with each other, and we don't know how to make those really massive black holes, and we don't know how to get them into binary systems. And so I think it's a really fun place to play around with different models, where you could get different answers for populations of black holes. And this is a cool one, because we do think we have a pretty good understanding of what kinds of astrophysical processes change the final mass of a star that could then collapse into a black hole, and it's quite hard to overcome those astrophysical limits. And so then we see these really massive black hole collisions, and we're like, well, you know, where did that come from? There are still, so it's neat to play around with physics ideas that can shift how massive a black hole can get, or how massive a star can get. But it's also important there to think about, you know, there are still other things that we don't know about the astrophysics that could change the picture, right? So these black holes could have gotten that big because of, you know, accreting a whole lot of matter, or merging with other stars in ways that we wouldn't expect, but could be happening in sort of clusters and things like that. So there's a lot of really interesting possibilities in terms of both getting a better understanding of the astrophysics, and then also having a new place to be creative with the physics. And so I particularly enjoy those kinds of projects, and seeing what can be done there. And my usual assumption is that it's probably going to be something astrophysics, because astrophysics is really complicated, and we don't have a really good understanding of all of it. And you know, if I had to put money on it, I would put money on there's something about the astrophysics we don't understand, rather than we've discovered a cool new physics thing. But I think we always have to try the cool new physics thing and see what it looks like, and find out how we can test it, and then you know, and then go on from there, because that could be the place where we're going to discover the new physics that changes our whole outlook on the standard model or whatever. So I think that's a really fun place to go.
That sounds like a really fun talk. I will absolutely have to go back and watch the recording of that, because it sounds really fun. Yeah. Okay, so we are almost approaching the time where we have to wrap up. We've been going almost an hour and a half now. So I just want to go around one more time and very, very briefly ask you what you're looking forward to the most in the conference. And for me, it's actually to be able to enjoy everything a bit more relaxed, because I had my plenary discussion today, which I was a bit stressed about. People who know me know that I just get stressed about everything. I just pretend it's part of the plan now. So I am looking forward to next week being able to enjoy the conference without having to do any more stuff like that. Anna, what are you looking forward to in the conference?
So unfortunately, I cannot relax because next week there's the discussion for my talk. Though it's not a plenary talk, so it's less stressful. But yeah, I'm just I'll try to. I'm looking forward to interact more with people because this is the 4th day. I've only had like I think like 1 or 2 social conversations on this platform, just because it's hard to just it's hard to find the right time to find people and interact with them. So I'm looking forward to do that and try to make some more connections in that sense.
I was muted. I'll drag you into some social conversations at some point. I think that's also something we do in in-person conferences where we just drag each other along. So we can do that as well and just tag you and make you appear in a room with us. Okay, Daniela, what are you looking forward to in the coming days of conference?
One of the things I like the most in a conference is the occasional light bulb moments that I get from listening to other people talks, trying to understand what it is that they did. And by doing this, I actually look at something, at some problem from a completely different angle and understand something new. Something else that I'm looking forward to is some discussion with other participants. So as you said at the beginning, conferences are really important. It's where the ideas are made. And I suspect there may be something that another participants and I might want to do together. I need to think about it more. Maybe it can't be done. Maybe it's not worth doing. But I'm looking forward to some more interaction on this point and really listening to all the other talks. And it sounds like the late time talks were actually, and the discussion was actually quite fun. So yeah, I'll give it a look and I look forward to the time when the discussion is also posted.
Nice. Alex, what about you? What are you looking forward to?
So my flash talk, which is very short, but it is a complement to one of the parallel talks given by one of my collaborators, goes live next week. So I'm excited to chat to people about the research that we've been doing and also just continuing to learn from a bunch of people about all of the interesting work that they've been doing and having good conversations.
Awesome. Sean, I know we already asked you this on Tuesday, so would you want to briefly again tell us what you're looking forward to?
Yeah, I might repeat my answer as well because it's a different audience. So we have a plenary talk by E. Rosita, who it was an X-ray telescope that was in space measuring stuff. And just like the week or 2 weeks before the conference start was when they released most of their information and data. So there was no actual cosmological analyses in that data release, but X-ray telescopes are very useful for cosmology. Partially for just narrowing down kind of some of the astrophysical stuff that needs to be sorted, but also they can do things. For example, they can measure the locations and centers of galaxy clusters very well and use that by measuring the X-ray temperature to infer their masses, which then becomes an interesting cosmological thing. So once E. Rosita becomes sort of one of the things that the conference participants are talking about, I'm very keen to see what kind of cosmology comes from that. We were quite lucky to have their data release so close to the conference. Will be the first major conference that is able to discuss that. So look forward to that next week as well, when we can talk about it in one of these live streams. Yeah,
that's going to be fun. Casey, what are you looking forward to in the coming days of the conference?
I'm looking forward to hearing a lot more about gravitational wave stuff. I don't work on gravitational waves really, but I'm fascinated by what we're learning from them. So I'm definitely keen to hear more about that. And I'm looking forward to some of the kind of separate, like ad hoc informal discussion things that have been proposed and that I'll be participating in. So those will be cool. And just sort of chatting with more people, maybe doing some more of those online games in our social times. Those are fun too. So we'll see.
Awesome. It's going to be a fun week of conference. I just want to remind everybody that tomorrow we're doing an Ask Me Anything. It's going to be running all day over on Reddit. And then in the evening, a bunch of us are going to jump on HAPS. It's most likely that I'm going to be around again. I can't let cosmology happen on HAPS without jumping on it myself. So there's going to be an Ask Me Anything that will start on Reddit, follow on HAPS, and of course going out to any social media because HAPS allows us to multicast. So we can link in our Twitters, our YouTubes. The Ask Me Anything will go out to everywhere because HAPS does let us do this. It should be on the Trenches of Cosmology account. You can follow the account. There's constantly posting comments here. Just feel free to follow, then you'll be sure to get the notification for the Ask Me Anything tomorrow. So I want to wrap up this session, and I just want to say a big, big thanks to the HAPS team for letting us take over the account and do this here today, because one of the reasons we're trying to do this outreach at the conference is to really bridge the gap between people who don't do science and scientists, and having such a platform and such a big reach to really be able to reach many more people and spread this message. I think it's super important. So huge thank you to HAPS for letting us do this. And thank you to everybody who's joined me up here on screen today. This has been awesome. We've had some really fun conversations, really fun topics. I will open the floor if anybody wants to make any final closing comments before we finish the broadcast.
Other than maybe re-advertising this AMA tomorrow, and just look forward to lots more things, because people were asking questions during the conference, during the stream, and we were unable to answer them because we had the slightly different theme. But tomorrow is the AMA time when we will be doing that.
Okay, thank you for that. So again, thank you everybody. Big thanks to the HAPS team. We'll see you all again tomorrow for the Ask Me Anything. In the meantime, have a great evening, everyone.